Alright, welcome to Complex Analysis by a Physicist, and in this video we're going to be covering Cauchy's integral formula, and we're going to be working through a few examples. Much like the Cauchy-Ghost theorem, the Cauchy integral formula allows us a really simple and easy, convenient way to evaluate some complex integrals. And naturally, again, per usual, with me being a physicist, I'm bound to do something to upset some of the mathematicians, but we're going to go through Cauchy integral formula. So let's get started. So the Cauchy integral formula is pretty straightforward. If we have a complex function that is analytic inside and on a simple closed curve or contour, depending on what you want to call it, that is positively oriented, meaning the path you're taking is counterclockwise, and z0, this z0 variable sits inside the curve, then we can use the following, okay? And so this is the Cauchy integral formula, and it works well for integrals of the following form, where we have a function in a numerator and then a z minus what we're going to call a z0 term in the denominator here, okay? And as long as we satisfy that the function is analytic inside and on the simple closed curve, that it's positively oriented, or the path is positively oriented, and z0 sits inside that curve, then we can use this formula, okay, to evaluate integrals. So let's look at an easy example of this. So here we have this integral, okay, and we're integrating our integrand about the curve, or about the path, mod z equals 2, which is a positively oriented circle. So we're obviously going to be going about this path like so, and it has a radius of 2. So it's centered at the origin of our complex plane, as a radius of 2, and it's positively oriented, okay? Now, let's identify each of the appropriate things that we need to check to see whether we can use the Cauchy integral formula or not, all right? Well, we know we have this closed curve, okay? We know that it's positively oriented, so that's one of the things done already. The other thing is we need to see what our function is. Well, our function is in the numerator, so f of z in this case is just z, and that is an entire function, or an entirely analytic function, so that checks off the box. And we need to check up on z0. Well, z0 is just simply this guy right here. It's just 1, so z0 is equal to 1, okay, which fits, which lies like right about here in our in our complex plane, which is inside of the contour, inside of the curve. So we can use the Cauchy integral formula, okay? And to do that, all we're going to do is we're just going to set that equal to 2 pi I times f of z0, okay? Instead, and because z0 is equal to 1 and f of z is equal to z, this just becomes 2 pi I. And again, apologies for the pi's. I write my pi's sort of like capital pi's. People have commented and say that it's weird, but that's how I've always written my pi's, so it's always how I will. But anyways, you can see that this does not necessarily look like a very friendly integral to evaluate, and we just did it in 2 simple lines just by identifying 3 simple things and taking a look at, the Cauchy integral formula. But the Cauchy integral formula that I introduced to you is not the full Cauchy integral formula. There's an extended form of the Cauchy integral formula which has all the same requirements, but this is what it actually looks like. You'll notice that the key difference here are these n's, okay? And this allows us to take a look at some slightly more complicated integrals, and really extends this out to the total amount of integrals that the formula is actually able to be applied to. And we can actually quickly take a look back, and the formula I gave you before is really just centered for n equal to 0. Okay, which so n right here is constituting a derivative. Okay, well, we're not taking any derivatives in the last one, which is just f of z0. So f of z0 is just going to stay the same. 0 factorial, okay, is just 1. So we have 1 on 2 pi I integral over the closed curve f of z on, well, we didn't have any exponent here, so it's just 1. So we just have z minus z0 dz, and you can see pretty quickly that we're just back to the older version, the first version of the Cauchy integral formula I showed you. But we can take a look at where the extended Cauchy integral formula is really beneficial for us. So here we have a very similar example to one that we did before, but now we have z squared, okay? We have z squared, and we're integrating about a positively oriented circle at the origin of the complex plane with a radius of 1, okay? And so let's identify everything just like we did last time. We see that our function in the numerator is just e to the z, and e to the z is, again, an entire function. All right, it's an entire function, or an entirely analytic function. So, you know, we can use, you know, that's the first part of the Cauchy integral formula, okay? The next thing that we need to do is we need to rewrite this integral in some sort of a way where we can identify an n and a z0. Well, we can just keep our integral mod z equal 1, and we can rewrite it as such, e to the z on z plus 0 squared dz. And with this, we can really easily identify that z0 is just 0, okay? Now, again, this is a positively oriented circle at the origin of our complex plane, and so 0, well, very clearly fits inside that. So that's another condition that's satisfied. So, you know, it's positively oriented. We know that. We know that our function is analytic, and we have z0 that fits inside that curve, okay? But now we need to take care of the n's because we need to be able to use this formula. Well, we can pretty simply rewrite this 2 here as a 1 plus 1, which gives us that n is equal to 1. Okay, and so we can apply the extended version of the Cauchy integral formula that you can see right up here. And again, we're just going to be multiplying this 2 pi I per n factorial over here, or really dividing it. So we're going to get a 2 pi I on n factorial, and then we're going to be taking the first derivative because n is equal to 1. So this whole thing ends up becoming 2 pi I on 1 factorial times the first derivative of our function at z0, okay? Which the derivative of e to the z is just e to the z. All right, so nothing changes. And then, so this is really in turn 2 pi I, and we can just, we're not going to include the 1 because 1 factorial is 1. And this just becomes e to the 0, which is just 1. So again, we're left with 2 pi I. Pretty simple, pretty straightforward, and again, with very minimal lines of work, we can evaluate this integral that might otherwise be a little bit nasty to evaluate. And that is why we love the Cauchy integral formula, because it makes integrating these sorts of things very easy, much like how the Cauchy-Ghost theorem basically tells us really easily whether or not an integral is 0, okay? So that'll do it for this video. If you found it helpful, feel free to leave a like or let me know in the comment section down below. If you have any questions, feel free to ask away, and I'll do my best to get back to you. And thank you very much for watching. These videos are supported by your viewership, and so by viewing this video, you're supporting me, you're supporting my work, you're supporting this channel. So thank you very much for watching, and I hope to see you again next time.